Hello, this is Fabricademy 2019, class 12 soft robotics, second part with Adriana Cabrera. Hello, Adriana.
Yeah, thank you so much. Yeah, I will continue the part that Lily starts, and we will just try to talk a little bit more deeply about what we could also do in the lab, and a little bit about the other aspects that are very important also about soft robotics. But first of all, I want to talk a little bit about how we could translate the softness aspect. So I heard also in your final project about, for example, emotions, about have soft reactions in our projects. So the technical work in physics about softness is compliance, and this work express, for example, some of the mechanisms about bending, squish, um, tensility when we are stretching, for example, a material, about squish when we are pressing, for example, a material and getting another in the same shape, stiffness or friction when we have, for example, materials that it can not break, but it can stays in the same shape. And this is what we are describing in compliant mechanisms that can be something that we actuate, that are behavioral mechanisms or behavioral compliance, or something that already have a compliance. For example, some hinges that we can bend and actuate. So we have several materials that we can use for prototyping soft materials or soft robotics. So we have a list about fabrics, for example, paper, TPU in several forms as foil or, for example, as filament, about silicone rubbers, but also we have with different, for example, shores. But we have also the opportunity, as Lily explained, that we can do our own materials in order to prototype our some robotics. So it's in order to have some robotics, we could also understand that our body is actuating as a soft or hybrid robotic when we have, for example, actuation and chemical reactions in our body. So in how it happens, for example, in cell tissues. But how we could actuate or sensing these characteristics, it's around, for example, other components as metallic films, smart memory alloys, shaped memory membranes or thermoplastics that can perform something, electroactive polymers, nylon, as Lily explains, or liquid materials. So basically, in this class, we are telling us as cooking robots. But we will start with some a small project, and also because we are talking about textiles, and um, this is a project that is from that it was published in the Kai conference in 2019 about making some actuations with fabrics. So as we know, fabrics at all, it's mechanisms that we can actuate, or it has as the form, for example, of knitting. It can also have this stretching and returning in the same form as the material is made. So for example, here you can embed other instructions or rigid instructions in order to have such interactions. Um, Also thinking about not only in parts that are electronical parts, but also parts that we can prototype and make, for example, some mock-ups or some wires that we can, for example, actuate or embed in the textile. So I put also paper, and I think that it's one of the old projects that I did in the past when I was a student at the Bauhaus University. So I was also in love about paper and origami folding, and also how to propose such structures, for example, for architecture. So I did a concept, and I did also my own paper, as we are doing biomaterials or paper making. So I embed in the paper electronics, and I embed smart memory alloys. So as you see, it's a very nice it's a very nice combination, because after I didn't take in the, especially in this project, but the paper enable us to take the components after a while, so that the paper can degrade, but at the end we can also, let's say, somehow recycling the electronical components. This is another nice project that it was also in the CAI conference in 2018 from the Morphine Lab. That is very interesting, and it's what the black part is just actually a filament that has graphene, the PLA that has graphene, and you see that connecting these filaments with current, you can get some kind of movement because of the changing of the current in the filament, enabling this kind of interaction. So after they decide, and because it was a very intuitive way to do such a interaction, or such a prototyping, actually you could also do by yourself, by hand, also using, for example, the doodle thing. They did a very nice workshop in which they did a kind of interactive books. I think that it could be a very interesting project for the ones that have some experimentation with several materials, or for example also with paper. Okay, we are now in another part that is about more about inflatables, about heating and sealing materials. So I just mentioned some of the materials that we can seal, like TPU or PVC. And this is one of the projects from the Fabricademy 2017 in Camp Linford under my skin, that tries to mimic animal reactions through air and try to express fear and, for example, happiness through galvanic skin sensor. And yeah, therefore the name under my skin from Estin Dumas. So basically, we are exploring folding and thermal sealing, thermal sealing and heating sealable hinges. So one of the nice of the great contributions around this area is from MIT Media Lab, that they try to experiment all of these patterns through sealing, but then they are using oscillating machine that is sealing the material, but actually we could do in several ways. What is important is try to understand which kind of mechanisms we can perform. So about twisting, bending, or maybe what could be also important for you if you want maybe to do just only a texture, for pressure lightly and gently the body, for example. So this is a very interesting technique, because we can use materials that we can wear. And basically what they are doing is sealing the hinges. In this part of the hinge, it comes not through the air. So let's say that if this is the part, let's say that I will seal, it means that I have to, let's say, put it in contact. So what they are doing is putting two parts, two TPU materials, thermopolyurethane, And I will explain a little bit deeper about it, how we are using also in the Fab Lab if you don't have the machine. But another aspect that is very important, for example, if we are not just making, let's say, these rectangles or diamonds, is the way how we are doing also the channels. So of course the thickness of, let's say, my lines or channels that I will design have also something very important to do, as I have here in the with the arrows. So you see that for example, if I have 60 degrees, how it will perform this movement, it will be less that, for example, if I have an angle of 90 or the 30 degrees, for example. Another part that is very important is about the pressure if I am changing the size of the channel. Why? Because here we are adding the pressure, the air pressure or the fluidic pressure through this way. It means that in between I have more pressure, then my material will also perform more, let's say, or will change the shape. So here we have some examples, for example, of shrinking and bending. The shrinking pattern, it's as you see, it can also perform very similar forms as the an origami pattern. That it's also very interesting to explore, and I encourage you to just try to experiment and do your own shapes. So by the bending pattern, actually, I did this through a research that I did in the past using processing and just changing, for example, the shapes or of the tree, for example, diagrams. So for example, here I have the changing of 120 degrees. And at the end, I get like almost like half of a ball, let's say, of the sphere. Another way how we could also do rotation is just adding one of or making like a small chambers using the baking paper, and this is something that I will now introduce. So for example, if we don't have any machine but we want to seal the material, what we are using is using a baking paper. So we find this as doing several thermo transfer in the t-shirts, and actually this is the same material that we are using for such a practice. We are using thermo transfer material for for t-shirts. So, but yeah, coming back to the picture, what we are doing is making these small foldings plus the paper, and what is producing is like these small chambers that it's also filling the air, and in that way my material can perform like kind of rotation. So how it works, what we have to have though, it's like these two parts of the vinyl, and in the middle to design our the channels where the air will flow. So after, what it is important is to have the allowance that the paper that the two vinyls will paste. It means that we are fusing both materials. It means that we are doing fusible interface, as we are, for example, doing also in other textiles. One of the most important parts is that we have to keep the channel of the chamber where we are blowing the air. So sometimes we are forgetting it, and of course after we have to open it, and it's also very important that you just keep a little piece in which you can just introduce the tube. So here is how it looks. You can also cut the material with the silhouette cutter or with the plotter cutter, as well as you are doing with t-shirts. And as I mentioned, what is very, very important is that you see that you leave the allowance for the material in order that you can paste both together. So just some tips. If you did this process before about printing t-shirts, so the part that you will seal, I mean, you see that this has this paper that this is like a kind of plastic that is special that can support enough temperature when you are pressing, and we are let's say putting both together with a temperature around 100 120 degrees, but this depends also of the material. It means that please be careful before proceeding to do this. Just look your material and see how much temperature you need for it, because it can happen that the temperature is too high, that after it is also melting the the baking paper. So yeah, exactly. So the temperature is around 100 degrees. The time 15 minutes. It depends, of course, in your depending of your material. And what we are also using is that to seal finally the whole construction, we are using shrinking tubes in order that the air is not going outside. Another technique that you can use is also laser cutting. And for the laser cutting, you have to do some tests also of how how uh, um, test of the settings in which settings I can melt my material. But of course, please use, there is also already, for example, some TPUs that are special for the laser cutter. What you have to be careful is that we cannot laser PVC because it will be also dangerous. This is a project from Julie Taris. She did the Fabricademy in 2016, and she did a very nice inflatable hood for bikes, and you see now it's just getting this impression of inflating, and how it starts to perform some movement, and that's how it looks the hood, and here starts to inflate, and it's very interesting because it can also you can think about like a kind of perfect fit for your head, as also, for example, in other projects, unfortunately I didn't mention, but for example LD Lazaro also implement some air, for example, structure for a bra, so having like, let's say, the perfect fitting. So this is another project from Harvard, but also complements with the activities in Amsterdam from the Amolf Institute from Bas Overwalde. He experiments a lot with structures with origami, and but more in a mathematical way, how these structures can also perform some movements, for example, transport things, how to do a 3D transforming material. So I think that also this could be at the end what we are doing is not really a material, it's a structure, but how to do these smart structures is what it's matter for this experimentation in this week. So another part of inflatables in a big scale, I wanted to share with you some of the examples that we explored in a workshop that we did for students in the Royal Academy of Art in Hague, that the students explore also with inflatables. That's some of the part of the exploration. So of course for here it's not enough, it's a simple model, we are using like fun, but it's very interesting to see how they just with simple, let's say, materials experiment to do big structures. And So this is the result at the end. They did that was also only 1 week of workshop, but what I found really interesting is that at the end they tried to experiment with this the inflatable hinges in a big scale, and how, for example, also people interact with the inflatable, so being close to it, playing. So it is exactly what we are trying to to communicate also with inflatables, that it's something that it's close to our body and that it will not damage you, and you could also let's say play in a collective, let's say, scenario. This is a project from um, also Tangible Media Lab group from MIT. The name is Preinflatables, and what they are trying to explore is also how in a big and small scale you can do pop-up, let's say, forms, as for example the furniture. So how you could also perform some objects, in this case, this small sofa, but also, for example, something that you can very easily have in a surface and after go to a volume. Um, okay, and now we are jumping in another topic, that is artificial muscles. So Lily explained us a little bit about artificial muscles, also introducing the the fishing line, for example, that it's also named as artificial muscle. So there are plenty of explorations about artificial muscles, in a sense, how, for example, our muscles works. This is just only a simple experimentation that is from soft machines recipes. Um, I will not put the whole video, but it's just a little bit about how I can prototype, for example, a small construction or animal. So it's very simple, because at the end you can just do with a piece of rubber and a piece of a sleeve. That actually is very interesting, because what we are doing with this textile, that is the sleeve, is constrain the movement that I have with my rubber and give a little bit more of the form. So I think that it could be also very interesting for the ones that want to explore, like perform like material, for example, or give a form, or let's say adapt to the body. Maybe this could be a start of an exploration. But it's a very simple exploration, and also you can combine with rigid parts in order to do uh, a very funny and interesting, let's say, yeah, maybe fab textile pet. Okay, so next one, it's related to what we talk in the past, that also Lily mentioned. But this is a little bit more in the other way around, as we were performing the last time. If in the last time we were talking about inflating something, here is the opposite. We are just trying to suck the fluidic that is inside. It could be fluidic, let's say, or it could be air, proper air. So what we are using is also a mixed structure, that it could be, for example, what we call like a skeleton or piece of paper. So for example, we did some small experimentation, but I didn't put also in the video. So what it's important is that you have like a piece of material that is inside, but it should be like that you leave that the air is flowing, therefore it has some holes. But as you see in the video also, that this experimentation is very interesting, in that it can also that is very nicely aesthetical, well, let's say appealing, but at the same time it has a very functional part, that it can also for example, be like kind of a gripper for food, or for example, until wheel, let's say. It could be very interesting to see if you can experiment. Okay, we are now jumping in another topic. Not like in the last slides, I talked more about foils and 2D shapes. Now we are coming in the part of the 3D model, and now it's about silicon and molding and casting. I will show you some of the projects of last year. Montserrat Sirius from the Salt. She did a very nice project, and also this could be also very nice exploration or example that you can also see deeper. She tried to do a garment that reacts also from people who is closer, and by, let's say, using by inspired design as basic principle, how animals react. So this is made in less cutting. So I will just go a little bit. Oh, sorry. I just will go a little bit. So that's the part also of the exploration of forms. And this is the final result. How it could also react and perform this feeling also of the animals reacting through these forms. Okay, so now what is important for this part as before, but now because we are working in a three-dimensional shapes, it's that we have to again have the control of the channels, as we did also in the past exploration with the paper and with the vinyl. But this time we have to respect a little bit about the thickness of the material. So, and this is also very important because the thickness of my chambers also will determine how much it will inflate, how let's say it will perform. For example, in this part, we have like 5 main channels in order to have a piece or let's say a body that can walk. So and each of these, it is actuated in a separate way, let's say, with independently motors. But let's look this through this tutorial that we recorded from last year. We have here this, let's say, the molds, and as you see, like, you have to leave a little bit more space, and also maybe do round edges in order that the material can also get better outside from when you are peeling the material. So you can do this 3D printed, but also you can do this with help of laser cutting. And cutting independently, let's say, the channels and the border. Yeah. So normally now I am using both two molds in order to have a better let's say cut of the one form with the other. It's not exactly necessary. But I can have through the cutting, I have a really nice control of the thickness of my material, as you explore in the last weeks doing biomaterials also. So because this is also a very important part, now is more important than ever, let's say, because if your material is not flat enough, or let's say if your mold when it's dry, when it's curating, it's not flat enough, then it can happen that it can inflate more in one side than the other. So here you see that we combine both rovers, and we use several rovers like EcoPlex or Dragon Skin that you can also use for your week of skin electronics. It is not exactly necessary that you use a release spray for it because it's very easily to take out. But what is important is that all the bubbles go out. Therefore, you can just keep, let's say, your piece and wait like around 60, like 1 minute that the bubbles go away. So you can put this also in an oven. What I did, or what for me works better, is that I leave one day. The rubber will curate. It depends which rubber you are using, but it curates around 4 hours if you put in room temperature. But this also depends of the temperature. Let's say the room temperature in each place could be that maybe in other places like in Brazil could curate in 2 hours, let's say. And after, when I have two molds, I can take one, I can put the mold in the top. I can just use the same material as I used before. So, and with this material, I will paste both. So that could be also one of the possibilities that you could do. Or we have also some adhesives that you can use for paste one and the other. So other variations that you can use is, for example, use textile. And the textile will help the soft robot to constrain the movement. So it means that we will put the textile in the under part of my soft robot. But what is important is that textile stays very flat on the surface, so that I cannot get like bubbles, or for example, as I said, that there are parts that has more rubber than the other. Another nice variation that you could do is use also color. So for the color, it's important that you mix the color in one of the rubbers. Why it is important is also because if you want to experiment and make, for example, drops on your robot, that could be also interesting. But the problem is that sometimes it makes a hole in your soft robot. It means that there it could happen that you have a hole after in your soft robot, and we don't want this. So, or maybe it could be that you want, but of course it will not. It will have some troubleshooting by inflating. Yeah. So yeah. Also, it is important that you don't have any bubble, let's say, in between the textile and the rubber behind, because yeah, otherwise it will also affect the model. And when it's dry, you can just cut the pieces if you didn't do the mold for the under part, and you can proceed to inflate. I am using a needle, but you can proceed to put directly the rubber. So also for other practices, for example, I am always putting after, and because of this, I put after the needle or after the tube. For other practices that someone is making soft robots, you can also leave the hole and after curate, but of course you have always the risk that it will be not sealed, let's say, hermetically closed. So you see that the textile is constraining a little bit more, let's say, the form. But another topic that we can also have is that with the air we can also get the chance of sensing. So it means that when I am pressing my soft robot, I can also use this as sensor. Okay, but maybe for you it's also interesting to understand a little bit about chores, and I guess that also Anastasia is very familiar with, or we talk a little bit about this in the textile as a scaffold, that in the shore it's a scale of hardness of rubbers and gels and yeah, silicones. So normally what we are using is rubbers that are in between shore of 30 and 50. But there are also other rovers that has also more shore. So in this scale, you can also find for each of the flexible materials that we have, also for the TPU, when you are buying also, for example, your material for prototyping, let's say for filaments. So you see that, for example, then you can understand a little bit like, no, maybe this rubber is very, very stiff, so I cannot use for my soft robot. Or maybe if you can use, you will need more pressure. So it means that you have to, let's say, measure this and understand how much pressure in terms of barns do you need for perform something. We have here several robots, but as I already mentioned, like Dragon Skill, Neocassil. So if you are using rubbers, as I said, that it could be more stiff, could be that you may need to use the vacuum chamber in order to get all the bubbles out, because in between the rubber is more, let's say, the viscosity is higher or the chore is higher, so you need it will be more difficult to get the bubbles out. The cell epoxy is as an adhesive for the rubbers, for the ones that we are using. This is very useful for the practices. We'll also take some headaches from the soft robots. Okay, I think that this is already we see it. Another nice practices that last Fabricademy starts to grow, let's say, is the use of fluidics. So you see, for example, this is an example also of the Monza. She did a very nice experimentation with fluidics, although here still is the air inside. So there is a little bit about physics inside of the, let's say, how to work with fluidics. It's almost just working with hydraulics and pistons, but we will not go so complex. It means that now you can just use the same way as we are using for the other robots with pneumatics. So another complex exploration is how, and I also encourage you to explore this, because sometimes it's very easy to cut, let's say, our molds, but we could also do actually a very precise and accurate molds also by 3D printing, in a way that we can also get other shapes. For example, in this case, that it's from the book Soft Robotics, that I try also to do is how you have your let's say 2 molds as you did in the past, but also in the middle you can also design this T part is the design of the channel that you after will take out, and after you will get this nice let's say finger for this gripper. So let me check. This is let's say here that you can after really have like a little bit more control of the form, and after, let's say, you can also combine with hard parts. So like this, let's say that now we are working as we are doing in wearables with hard and soft parts. So now we have to do the same, but with soft robots. So it means that, by designing 3D shapes by 3D printing, or we can also explore a little bit more again how to do this behavior in rotating, bending, or a bidirectional actuator. We have other practices that we can also directly print our material. So there are already some materials that are flexible for SLA, but are not elastic ones. So it means that probably we have to be very careful that our material doesn't break. So this is one of the examples that we did also last year in Form Labs, trying to, let's say, combine this design for the Disney research for the fingertips of the Vmax. Yeah, and as you see, it's very interesting because for the ones that are interested in do something close to the body, just pressing it a little bit can get also. I can also do a very nice sensor, let's say for yeah blinking something or actuate something. And this is an exploration that it's also from that you can also find in the Soft Robotics Toolkit about 3D printing with silicon, and it's also closer well printing also biomaterials. How you can also get a 3D printed shape. So I have, for example, this one that is also 3D printed with silicon, and also you can get a very nice, wait, sorry. Shape up of it. What is interesting is that by 3D printed silicon, you can also regulate a little bit more about the thickness and about the let's say properties of your material without being too thick. That is also the, let's say, the main problem and troubleshooting with the silicon rubber and molding and casting. But another practice that it could be very interesting, and what I like from this class is that you can also combine a lot of the resources that you already use for your for the first classes as biomaterials, is that you can also prototype a sensor, or no, sorry, a soft robotic that is out of bioplastic. So I just want to just shortly show this, that it's one of the projects from Festo, that it's a mixed robot because it has also rigid and soft parts. It is a combination also with textile, but inside is also that it's also constraining the movement, but at the same time it has also the channels for the air. So you see that there are also combining sensors around the forms, and also distributing the air from two air chambers. And of course, it is another mechanism that maybe is more complex about the piezo valves. But let's say that it's only just to show you how it could be a complex project from soft robotics. So we are coming in the part of the control. This is also one of the boards that the Fabricademy students from 2017 did. Wei Shang, she did a very nice device for anxiety, actually, for people who suffer anxiety, and the air brings, or let's say this lightly pressure brings a lot of benefits out of it. But what I wanted to tell and just simplify, because we don't want that what we want is that you experiment with all of those resources, is to understand that all of those mechanisms that we have, being fluidic or being air, it's very, let's say, simple. So we can work with air pumps or peristaltic pumps and the valves that we need for controlling the system, so open and close the air. So all of those work the same as DC motors. It means that what I need is just actually these connections that we have here with the transistor, so that it helps us to provide more current to my system, let's say, with that it is a very simple schematic how you could connect this to the Arduino and to the motor. And probably you will need also a bigger, you need a more, let's say, a power supply. It means that probably you need several, let's say, you can provide, for example, 12 volts for a bulb. So it's something that you can also very well provided in the Arduino. So by using the bin, let's say. But if you have questions, just let me know. So we just wanted to keep simple as possible. So there are also other boards. I don't want to go so as I said deeply on it. But for example, just to mention that here we have we need just only the connection of a valve and a pump, and for example, this is a schematic that I did for the for a workshop that I did in Qatar, and it's just simply connecting these two parts, the valve and the pump. But also there is also other valves that are also developed and more expensive, unfortunately, but I think that in the lab you can prototype in a very easily way of these connections and do your own, let's say, boards or your own construction in a very simply way. So, and here, for example, is one of the enclosures or one of the adaptations that we did for the Fab Lab conference in Fab Egypt for enclosure of a mini pump and the construction of the transistor in a small enclosure. So it means that please don't be afraid that it can go so big as for example it is here in these images. So of course maybe for this construction, if we want to pump, I don't know, a dress, it will be of course more challenging than for example just a small gripper, but it's something that that it is possible, let's say, or it is doable just to split in, let's say, the chambers or making it in a different way. So just to conclude, of course, there is also software that is making simulations also for soft robotics, as for example, Grasshopper with the plugins of Kangaroo and FlexHopper to simulate the shape of the soft robotics as from the, let's say, three-dimensional shapes, as for example the folding patterns. But something that is important to mention is that all of those softwares are made for standard static volumes and solids. So it means that it's a very big challenge to understand how we could simulate it in a software. Therefore, it's not the most easy part. Therefore, we are not going so deeply on it. But there are already people who is working, let's say, very tough on it. As for example, the group that is working in FlexHopper. Another point that I forget to put, but is in SolidWorks we have also the software of Simulia, and this is also a software that is trying to get inside of soft robotics or such volumes. So for the ones that are in Dachau, they can also maybe try to explore a little bit deeper on it. And now it comes the better part, the assignment, and due that we see that we have several techniques, so we would like that you make at least two of your design, that it's also important that it's your design, that you try to understand and to make your own soft robotic based on the techniques that we describe. It could be fabric, it could be paper, it could be inflatable in a big scale, it could be inflatable in a small scale, it could be a rubber with molding and casting or 3D printing. You can also experiment with a biomaterial or a mixed shape. That is also important that you try to actuate or let's say or make it at sensor, document the trouble and shooter, and make a video. So it is also the part optional if you want to integrate all the electronics. But of course, we will be more than happy to support you and hear about your ideas in the next week. So we have some resources that you can also find online. Of course, this presentation is available for you and have already Anastasia and Cecilia. So if you need more information, just look at it. And thank you so much for all people who was also collaborating in this week, and yeah, that makes also all of this experimentation possible. Okay, thank you for your attention. Maybe do you have some questions?
Questions? A typical question is it mandatory that they do the electronic circuit with a pump?
Well, it's what do you
I
think?
have the answer. I have the answer. It is yes, you can do the electronic as a collective assignment. All together, you make one board that works with the pump so that you can test. So all of them together. Yeah.
Okay. Yeah, I mean it's important that you try at least to do the I mean to try to pump it, but we already show also other resources, no? So
Yes.
I think that
Or
yeah.
suck it.
Or suck it.
Yes.
Or sensing.
Yes. Okay. Thank you so much, Adriana. It's very, very inspiring. I think that now they will all change their final projects with this. So, yeah.
The robotics.
Anyway, yeah, see you next week. I will stop recording.
Okay.